Now we'll look at a method of determining whether or not a sequence converges or diverges, not by examining through analytics, but really just kind of observing patterns through their graphs. And that's not always going to be something that can be relied upon, as we saw in a previous example. But if you can easily determine a couple of different properties, then this is something that could tell you if a sequence converges or diverges. So the properties that we're going to look at begin with a property called monotone. So a sequence A sub n that is non-increasing or non-decreasing, and non-increasing and non-decreasing, what that means is that it's either always increasing, always decreasing, or constant. So a constant sequence would be non-increasing or non-decreasing. So if that happens for all values of n, your subscript, greater than or equal to some given subscript, it doesn't have to begin at 1, it doesn't have to begin at 5. As long as this pattern happens at some point, we can call it monotone. So for instance, here's the first sequence we'll look at. A sub n equals 2n plus 1. Now, I think we're familiar enough with what that would look like so that we don't need to really pull up a chart or anything. This is going to be a linear function, so the points of a linear would increase in the pattern of a line. So this pattern would always be increasing. And if it's always increasing, then we can say that it is monotone. All right, simple enough. Okay. Let's look at this next example. So I have 2 plus negative 1 to the n. Now, this one you might not be quite as familiar with what's happening, but here's the idea. So when I let n be 1, it would be 2 plus negative 1, which would be 1. When n gets to 2, it's 2 plus negative 1 squared, which becomes positive 1. So 2 plus positive 1 is 3. When we get to x equals, or n equals 3, 2 plus negative 1 to the third would be 2 plus negative 1, which would be 1. And then the pattern would just continue to repeat in this form. So the thing is, it's increasing from one point to the next when you have even values, or actually odd values, and then it's decreasing, then it's increasing, then it's decreasing. It's flip-flopping, it's oscillating here. So if it oscillates like this, and I think there's 2 L's there, but anyway, it's not a monotone sequence. Okay, let's look at the next sequence, 1 over n. So 1 over n, what that would look like is kind of like the inverse of a logarithm. It's got an asymptote here at 0, but we're starting with 1. And these values would decrease to a horizontal asymptote at 0. They approach it, but never actually run into it. But this would be always decreasing. And if it's always decreasing, then that is monotone. So as long as you can see the graph, you can generally determine pretty readily if something is monotone or not monotone. If you're unfamiliar with the function, you might need to rely on some sort of technology to draw the graph for you. So let's do that here. So in this example, we had the sequence n squared divided by 2 to the nth power minus 1. All right, if I draw this sequence, here's the pattern I run into. And it's rather interesting because it starts off increasing, but then it reaches a maximum at some point and it turns around and it starts to decrease. Even if you drew this as a function, you would see that pattern. So it reaches a maximum and then it starts decreasing. But the thing is, it's monotone if you cut off the first so many points, which in this case, I suppose if we cut off the first point and the rest of the points are monotone, then we can call it monotone. So this pattern does work as a monotone sequence. So since our sequence looked like this, we had an initial point, then it went up, and then it started to decrease after that. This was decreasing for value of n, which is greater than or equal to 2, and then therefore we could say that this is monotone. And we could say for n greater than or equal to 2 if we wanted, but this qualifies as a monotone sequence. Okay, so determining if a sequence is monotone is helpful in determining whether or not the sequence is convergent, but it's not everything that we need to know. We also need to know about bounded sequences, and this should actually just say bounded sequences for here. A sequence is bounded above if there exists a real number m such that a sub n is less than or equal to m for all positive integers n. And it's bounded below if there exists a real number m such that m is less than or equal to a sub n for all positive integers n. And then we say it's bounded if it's both bounded above and below. Otherwise, it's an unbounded sequence. So let's take a look at this previous graph that we had and see what that means. Okay, so if we have a bounded sequence, then that means there's some maximum value that the sequence never goes above and some minimum value that the sequence never goes below. Now, there is a called like a maximum value that it reaches, but that's not really important to us. What's important is that there's some value that is larger than all the values in the sequence and some value that is smaller than all values in the sequence. That tells me that the sequence is bounded. It has to be bounded above and bounded below. So unlike the sequence 2n plus 1, which was our linear sequence, I guess I'll have to change my scale here to see it. This, even though the sequence is bounded below, so there's no values less than, looks like 3, y equals 3, so it's bounded below, it's not bounded above. Every single value that I choose for a bounded value above all these points, I will eventually find that there are other points that are larger than that. So if I said that this was my absolute maximum, it didn't go beyond there. Well, unfortunately, if I scroll out further, I'll find that there are points larger than that. So this is not bounded above, which tells me that the sequence itself is unbounded. So as long as you know what the sequence looks like graphically, you can generally get a good idea if the sequence is bounded and if the sequence is monotone. And we have a theorem here which states that a sequence that is bounded and monotone will converge. And it's as simple as that. If you can show that the graph or the sequence itself is bounded, so it has an upper bound and a lower bound, and it's monotone, then we know it will converge. Be careful, because this is not a two-way street. It does not mean that if we have a convergent sequence that it is both monotone and bounded. And I'll show you an example. But if it is bounded and monotone, it will converge. So for instance, the sequence 1 over n, which we saw as a sequence like this. All right, we determined it was monotone, and there is a maximum value above all the points and a minimum value below all the points, so it is bounded. And because it's both monotone and bounded, this sequence converges. All right, and let's look at the next one. So here we have a sequence, and this was from earlier, that looked like this. It is bounded. Okay, there is a value that's larger than every single term in this sequence. And there is a value that's smaller than every single term in the sequence. So it's bounded, but it's not monotone. And what we can conclude here is that, well, actually, we would have to do different testing, but this right here actually diverges. You can't really use this to determine if it's convergent or divergent. You can't really use this theorem to prove divergence. The thing is, we have another example later that is also not monotone. It's bounded, but it converges. So you can't, it doesn't really prove divergence here. You have to kind of go with other methods at that point. But in this situation, because this oscillates, we're never going to approach a single value, so we can conclude that it diverges. All right, this next one, which is a linear function. So linear functions would always look like this. Certainly be bounded below, but as we saw, they are not bounded above. Or it could be the opposite way around. So this is not bounded. Okay, but it is monotone. All right, but if it's not bounded, that is enough actually to say that it's going to diverge. Okay, so if you have a sequence that's not bounded, it's going to diverge. There's no question about that. All right, last one here, -1 to the n over n. So let's take a look at what that looks like. Okay, I have -1 raised to the nth power divided by n. And I guess I'm going to have to probably reset my scale here. Let's bring this line down and zoom out this way. That way we can get a good picture of this. Oops. Okay, now this particular graph, if you'll notice in this sequence, we do have a maximum value and a minimum value. So if I set these lines here and here, all the points in this sequence are in between those. So that tells me that this graph is, in fact, bounded. All right, monotone. The problem here is from this point to this point, I increase. Then I decrease. Then I increase, decrease, increase, decrease, and so forth. It's oscillating. All right, similar to the example 2 to the -1 to the n. It's oscillating. But the difference here, even though this is oscillating, it's not monotone, but the values are actually converging. So we can see that these values are converging. They're actually converging to 0. So if we kind of zoom out a bit, we can see these points getting closer and closer to 0. So here's kind of a counterexample to the point that I brought up earlier. So here, just to draw it for you, we have this sequence that looked like this. So it was kind of flip-flopping. We definitely saw that this thing was bounded. But it was not monotone. So here's the thing. Earlier, we had a sequence like this that was bounded, but not monotone. It diverged. Here we have a sequence that's bounded and not monotone. That's converging. So here's the thing. Again, you can't use this if the theorem only works for sequences that are bounded and monotone. That proves that it will converge. If anything else happens, you can't use this theorem for proof. You have to use alternate methods.